Hi guys, so today we're going to look at applications of rate of change. So I'll just go through one example here and then do an example for the first question in the exercise 18b, which is what we're working on. So to find the rate of change at a point, as we know, we would just need to differentiate the equation and substitute in that point, because rate of change is the same as gradient, and to find gradient at any point, we just need to differentiate. So here is the question. So we've got a balloon is leaking, so its volume is given by V is equal to 600 minus 10t minus 1 and 100 t squared. Obviously, and this t is greater than 0 is the domain for which this exists. Obviously, if t is less than 0, that's not possible because t stands for time. Okay, so first thing to do in any of these questions is find the rate of change after however many seconds. To find the rate of change, you need to differentiate in terms of volume and time. So dv on dt, so you're differentiating, just like when you're differentiating y in terms of x is dy on dx, this is dv over dt. So change in v over change in t. So the 600 obviously goes away, that becomes negative 10 minus, bring the 2 times by 1 over 100 is 2 on 100 or 1 on 50 t. Okay, and now that is the rate of change at any time. Okay, so part I is when t equals 10, what is the rate of change? Okay, so all you need to do is substitute in t equals 10. So the rate of change, dv on dt, is the rate of change, is equal to negative 10 minus 1 on 50 outside of 10, which is equal to negative 10 minus 10 on 50, which is 1/5. So it's equal to negative 10 and 1/5. Okay? So i.e. the balloon is deflating at negative 10 and 1/5 centimeters cubed per second. Okay, so I'd like you to pause the video and have a go at part 2, which is looking at when find the rate of change after 20 seconds. Okay, so it's the same approach. When t equals 20, dv on dt is equal to negative 10 minus 20 on 50, substituting in 20 for t, which is equal to negative 10 and 2/5. And then, i.e. the balloon is deflating, I'll just do ditto marks there, at negative 10 and 2/5 centimeters cubed per second. So the rate of deflation is actually increasing as the more time passes between 10 and 20 seconds. Okay, part B asks us, for how long will this model be valid? Okay, so this model becomes invalid once all the volume is out of the balloon, so when V is less than 0. So we need to find when V equals 0, to find that point when it becomes invalid. So when 600 minus 10t minus 1 on 100 t squared is equal to 0. Okay? This is in a quadratic form, which would make you think quadratic formula. It's just in a different order, so the coefficient of the squared term is a, coefficient of the regular term is b, and the last one is c. So t is equal to negative b, which is negative negative 10, plus minus square root of b squared, so negative 10 squared, minus 4, make sure you have that outside the brackets, times by 1 on 100, times by 600, all over 2a. Okay, so 2a would be 2 on 100 or 1 on 50. Okay, I would just put that in your calculator as it looks there, and you'll get t equals negative 1056.78 or t equals 56.78. Okay, so this one can't exist because time can't be negative, therefore the model exists from 0 less than between 0 and 56.7a. Okay, I'll do one more example in the next video if you need another look, looking at question 2 in exercise 18b.